So
Hello.
hello everyone. Thank you so much for the IUPAC webinar series organized with Camera. My name is Juliana. I'm a senior program manager at Beyond Benign. Today we have an amazing speaker and also an amazing moderator. Lavish is here with us. So I'm just going to stop talking and give the floor to Lavish so he can introduce you to our webinar. So thank you so much for being here.
Thank you, Juliana, for this. And today we are going to have an interesting webinar on affordable, equitable, clean water availability and materials-based approach. So the professor is expert in this field, and we'll listen to him about this facet that fosters the narrative of sustainability in the field of chemical sciences. We welcome you all and hope for interactive engagement during the event. So first, before we begin, we would like to have a brief introduction about IUPAC. You know all that we are famous for naming elements, periodic table, atomic weights, nomenclature, terminologies, technical reports, and lot more. So IUPAC as in needs no introduction in that sense. So we are aimed at uniting global chemistry community for the advancement of chemical sciences. This webinar is a part of IUPAC Cameron project, which stands for Chemical Research Applied to World Needs. Our work is tied to United Nations Sustainable Development Goals, and there are a few activities you can see that are part of our IUPAC Cameron project. This include global conversation on sustainability, chemistry entrepreneurship project, and as well as this webinar series that we are organizing. So I represent IYCN, International Younger Chemist Network, and that is where we are committed to make an inclusive and welcoming environment for all those young chemists who are in the field, and run by young scientists. We all are, mostly below 35 years of age, and function as a cohesive unit of to foster the dialogues among youth, young chemists, and as well as experts to build their capacities and uh, a few uh, narratives that needs their introduction. So we have members all across the globe and are always looking to welcome all. So this is the project Global Conversation on Sustainability, and so it's an annual event organized by IPSC, ISC 3 Beyond Benign, and including IVCN as well. This is a commemoration of the adoption of Sustainable Development Goals agenda, and in this context, we invite speakers from all across the world to talk about sustainability and how we have been progressing in it, particularly in the field of chemical sciences. Now I hand over to Ju for the introduction to Beyond Benign.
Thank you, Lavish. Yeah, so if you're not familiar with Beyond Benign, who's partnered with IUPAC Camera on this project, we are a nonprofit dedicated to green chemistry education. We have a lot of projects, initiatives. So if you want to keep in touch with the work we're doing, please scan the QR code here on your left. And we also have a webinar series coming up in October 15th that I'm going to talk a little bit more about it at the end. So yeah, just connect with us at Beyond Benign, please. Thank you so much, Lavish.
Thank you, Anju. So this is again a bit about the project goals, which Beyond Benign is also a partner in that IPSC Cameron project only that are this webinar series is based on SDGs and IPSC top 10 emerging technologies, which you'll see in the later slide. We are also aiming to develop short videos for different audiences with different chemistry backgrounds. So you're most welcome to outreach about it. And these are the top 10 emerging technologies. So you can also participate by giving your votes and telling about which technology should be in the should be featured in the IUPAC's list of top 10 emerging technologies. And in 2024 we have these technologies which were listed. Now coming to Professor Subramaniam. So since we are going to hear him, let's have a brief introduction about him. So he is a professor of chemistry at IIT Bombay. His research spans photon-phonon energy conversion, solar thermal materials, electrochemical energy storage, wearable sensors, and operando methods for probing electrified interfaces. Earlier, he has worked on carbon nanotubes during his PhD and developed nanocomposites for semiconductor application at AIST, Japan. He also founded a startup focused on solar thermal coatings. He has received several honors, including the IUMRS Young Scientist Award in Gold Medal, the Iijima Award, Japan, and the DST-SwarnaJayanti Fellowship, and IIT Bombay's Excellence in Teaching and Impactful Research Awards. He is author of 75 plus peer-reviewed papers and 20 patents. He also served on the early career board of ACS Sustainable Chemistry and Engineering and as associate editor of the Bulletin of Materials Science. There is a lot to talk about him, but since we have limited time, so I'll directly hand over to Professor Subramaniam to take it further. We welcome you, sir.
Thank you. Thank you so much, Lovesh, for contacting me, reaching out to me for this wonderful opportunity. And thank you to the IUPAC and the Beyond Benign group as well for giving me this platform to kind of share some work which we've been doing, which towards the end, I hope I'll be able to justify that it's also in the path of sustainability. I'll just try to IUPAC. By the way, the first time I came across IUPAC was in my 6th or 7th grade when we were exposed to the name nomenclature, and since then it has been an integral part of my career. So it's really an honor to be a part of this and share the platform with IUPAC. So thank you so much for that. Oops. I hope. My screen is visible.
Yes,
I've
sir,
shared my
screen
screen.
is visible.
Okay. Thanks a lot again. So what we are going to talk to you about is, like I said, some of the recent research which we are trying to translate it forward. I'm disclaimer right at the start that I'm not. I don't think we have the solution entirely yet, but we have made an opening and we are in the path towards developing a solution. This is related to the clean water availability and accessibility. I'm coming from a material science background. My fundamentals are in chemistry. I work a lot on materials, so I'm trying to kind of view this entire topic of water and cleaning and purifying water from a material science perspective, and that is what I thought I'll share with you today. So again, a little bit introduction about the place that I come from. This is India, and this is IIT Bombay, stands for the Indian Institute of Technology Bombay. It's on the western coast of India, and it's a beautiful place, about 500 acres of campus, lush green, especially during this time of the year. Beautiful campus infrastructure. The good thing is you can find a variety of not only vegetation, but also beautiful birds and sometimes scary animals as well, as you can see from this leopard, which has been caught in a CCTV camera. The best part of it is it's completely residential. That means all the faculty, which is about 750, with their families, about 18,000 students, everybody stays on the campus. So it's basically a mini township. It's fully residential, and that's what gives the entire energy and vibe to the campus. I invite you to come and spend some time whenever you're down in India or happen to transit by Bombay. Please do let me know. I'll be happy to host you. So again, since this talk is centering on sustainability and what chemistry can do for sustainability, I thought I'll flash this slide first. The United Nations Sustainable Development Goals. Basically, these are goals which we have given to ourselves to see and transform the world around us, to make it more sustainable and pass on a beautiful world that we have inherited from our ancestors to the future generations. And these are if you look at the 17 goals that we have given us, almost 7 of these 17 goals relate to food, energy, water nexus. That means the availability of food, water, clean water becomes an important aspect, and the water energy nexus, therefore, which is built around it, becomes integral for us to move towards or transition towards a more sustainable environment and a sustainable earth. So in this direction, if you see water, and ask this question: do we understand what is water apart from its chemical formula of H2O? Do we understand water really? If you ask this very critical question from a scientific perspective, the answer, I'm afraid, is no. Water has been consistently throwing a lot of surprises at us. The more we research into water, the more surprises unfold. Say, for example, this is a beautiful review which came out in 2006, which talks about the density of water or the structure of water, especially at interfaces. And you see that the density of water, which is in the y-axis, can be, it need not be one, as regularly as our textbooks say, 1 gram per centimeter cube. It can be all the way from about 0.2 grams per centimeter cube, which means that the packing structure, everything is so very different about it. And it can go even beyond one, which means that it is, you can get a lot of densified water. And all these are water in liquid states, by the way. So the density of liquid water, of course, bulk water is, we know a fair bit of it, but water at interfaces, especially when you're talking about cleaning water using interfaces, any kind of filtration, any kind of membrane-based filtration or adsorption-based is really acting on water at an interface, at a heterogeneous interface. So, and now we start to see that even and again, for this, for example, this work from Andrew Geim, who got the Nobel Prize for his discovery of graphene, has reported in Science that the bulk water, we know that the dielectric constant is about 80, but it can go as low as about 1.8. So this is again, water behaves extremely differently at when it is at really at an interface. And again, something in Nature which came out as recently as 2021 started looking at water as a metal, water which has a huge number of electrons being pushed into it. Beautiful extract of a very, very counterintuitive experiment where you can just write reaction of sodium plus water giving sodium hydroxide. They did the same experiment, but then started looking at metallic states of water. So if you really go into the real interfacial properties of water, what I want to convey or impress upon the audience is that the structure and properties are largely unknown, and a lot of surprises wait for us in this domain. So now, with that as a background, if you look at the contaminants of water, of course, there is an innumerable number of contaminants because of all these properties. You can get, you can basically think of anything and everything, and water will have it. A given set of water will have that. These are some of the few contaminants. So again, a very, very constricted and illustrative list. But what really is coming out from this is, if you want to get clean water, if you want to purify water or clean water, the problem is so very complex that it cannot be done by just chemistry or physics or biologists alone. In fact, what we want is science as a whole and technology as a whole to come together to get this pure water. And that is what we are trying to lean towards as the rest of my talk, in the rest of my talk. So again, something about a little more about water is about the total volume of water on Earth is about 10 power 21 liters. This is fixed. So every single water molecule that you find on Earth is coming out from this 10 power 21 liters. And again, the freshwater availability out of this is extremely low as about 4%. So we need to really think of pure ways of purifying water. And how does nature deal with this? Nature has its own beautiful hydrological cycle, or the water cycle, which is basically evaporation process followed by condensation and precipitation, which kind of recharges. And this is how the water cycle or the hydrological cycle evolves. And but here, if you see, the interesting aspect is evaporation is a energy demanding process. That means if you want to take liquid water and make water vapor out of it, you need to supply energy, which is roughly about 2000 joules per gram of water. And the same energy that is supplied by us to the water body during endothermy during its evaporation is actually released back when it is forming clouds and precipitating down as continuous rain. And this is how the energy balance along with the mass balance is treated in nature. And but if you look at the overall, like the Earth as a huge living lab, and try to see what is the rate at which water forms clouds and reprecipitates as rain, it's about 1 liter for every meter square area of the Earth in 1 hour. That's the amount of water that is actually evaporated and then falling down at some point of Earth at any given point of time. So somewhere in the Earth there is rain at any given point of time, and this is basically the rate at which the water evaporates and falls down. And the important thing about this entire beautiful hydrological cycle, which has been operating for as long as the Earth, is basically the evaporation of water leads to water vapor in its purest form. Leads to water vapor generation, which is the purest form of water. Irrespective of what source of water, you can think of the most dirtiest form of water. Once water evaporates, it is as water vapor by absorbing that 2000 joules per gram. This is the most purest form of water. Therefore, the only limitation to this entire natural cycle, naturally happening ubiquitous hydrological cycle, is that the kinetics is extremely slow. Nobody wants to wait for 1 hour to get 1 liter of water, or in a course of a day, 24 hours, when the sun shines, you probably end up with 5 to 7 liters of water, and that's too small for the kind of population that we are the Earth has right now. So that means the kinetics of the hydrological cycle is really slow, climate dependent. So these are things which we want to take up as a material science challenge. And we have kind of mimicked we've kind of mimicked the natural hydrological cycle in these devices which are called solar stills, where you take dirty water, use the solar energy purely, the heat from the sun evaporates the water, condenses it back through this at the backside of this glass surface, and then you can collect the condensate water, which is the almost similar impurity to deionized water, because it's going to contain extremely low ionic salts or any other kind of impurities. But the intrinsic, this has been there with us for almost 6 to 7 decades. With civilization. But then the problem is, if you look at it from a very wholesome picture, you see that the light admitting surface, which is the glass surface on the top, is exactly the same surface in which the water vapor actually condenses. So in the top surface, this is where the light penetrates, from sunlight penetrates, ends up in heating the water. And once the water evaporates and forms water vapor, the condensation starts to happen on the same surface. This means that this is going to be a self-limiting process, because once you start forming water drops, you're going to attenuate the light intensity which is going down, and therefore the heating and the water vapor production starts to naturally decrease. So this is now a kind of a vicious cycle or a self-limiting process, because of which we are not doing any way. These devices won't do any better than nature, which is about 5 to 7 kilograms per meter square per day. That is about, you get about 5 to 7 liters of pure water in this as condensate. And if you look again at that, like I told you, the condensation is an exothermic process. It releases heat, which again adds to the efficiency loss. In fact, if you do an energy balance, the heat used for distillation, which is the water vapor evaporation and condensation, is just about 38 or 40% of the total energy that is available from the sun. So this is really the crux of the problem, that there is an greater energy efficiency that is required to bring about better and faster through higher throughputs of clean water from solar stills. So this is the problem that we started with, and said, okay, what do we do? If you look at the solar spectrum, this is basically starting from 250 nanometers, you can go all the way up to 2500 nanometers. This is the entire spectrum of light that the sun throws at Earth. And if you look at solar panels or any kind of photo-driven process, they try to utilize part of the ultraviolet region and a large part of the visible region. Thereby, they actually do have preventive mechanisms in place to avoid the infrared radiation, which contributes heat. That is the first thing that you do, especially in a country like India. You step out in the sun, you see that it's extremely hot. So the infrared radiation is actually never a part of these technologies, which was very surprising to us. And we said, can we capture and utilize the entire range of solar spectrum instead of being partial to the ultraviolet and the visible part? Can we include the infrared radiation and start to utilize that as well, because this part of the radiation actually contains 50% of the solar energy. So by restricting ourselves to ultraviolet and visible region, we are only working at 50% efficiency straight away by ignoring the or neglecting the infrared component. So for that, we needed materials. So what is the material? We started with something like these are structures which we form in our lab that are completely made of silica. The reason why this structure was appealing or interesting to us was basically you have this beautiful structures when you see through an electron microscope. You have this fibrous kind of structures. It almost looks like a sea urchin with a lot of tiny spikes pointing from a central core. And this is what was in the structural aspect of it was, or the morphological aspect was interesting for us, which means that it can have a large accessible surface area. Of course, it's made with completely SiO2 silica, which is extremely thermally stable, but it's optically inactive. So it's white in color. Pure silica is white in color. So has nothing to do. In fact, it is everything that we don't want when we start looking at the entire solar spectrum, because it's optically completely inactive. So now what we do is we take this material, want to leverage the morphological aspect of this, and therefore we cover this or coat this with carbon. And we do this through a process of chemical vapor deposition, where you send in acetylene at high temperature. Acetylene, by controlling the conditions, is the carbon source, and you can start depositing carbon all along the silica walls. And once you do that, you can conveniently remove the silica, because SiO2, you put it in an alkaline medium, sodium hydroxide or potassium hydroxide, it dissolves by forming silicates, sodium silicates or potassium silicates, and those are completely soluble in water. So you kind of use this silica as a template, and what you get is a complete dedicated reproduction of the template, but this time it's entirely made up of carbon. And these are structures which, when we initially formed, we thought it looked like something like a marigold flower. So we decided to call them nanocarbon fluorides. If you see the electron microscope and compare it with this, it's exactly an identical replacement of the entire structure, reproduction of the entire structure, except that every moiety of SiO2 here has been replaced by a carbon matrix here. So this is now an all carbon structure, which appears in the form of fluorides, and therefore we call it as nanocarbon fluorides. And we have optimized the conditions so that we can make very large scale. We can make kilograms of this in a given batch, in one batch, and it's extremely monodisperse and solution processable. So what do we do with this? We, like I said, this is the structure that we have, and this is again, when we make it, we get it in the form of a solid powder, which we then process and make it in the form of a dispersion or a paint. So, and this gives us the flexibility or the versatility to coat it on a lot of different substrates. So, for example, you can coat it on the wall of a building like a terracotta or a cement structure. You can coat this. You can coat it on copper sheets, metals like copper and aluminum. You can even coat it on filter paper. And the first observation that we see is extremely black in color. Any substrate on which you coat is extremely black in color, and that is actually reinforced by these absorption or the transmission spectra, where you see that the coated material is completely doesn't transmit any light over the entire solar spectrum, starting from about 400 nanometers, which is where visible starts, all the way to infrared. It absorbs a lot of this the photons. It's about 95 to 96% absorption of the photon that happens with these coatings. And what the next question is, what happens to these the energy? Because when it absorbs photon, it means that it absorbs the energy from the photons, the light photons. So for that, we kind of looked at the thermal image. thermometric imaging, try to measure the surface temperature. So for example, this is the surface which is put in dark. The minute we put it in sunlight, you see that the surface temperature shoots up, as shown in this red image, and it reaches almost up to 150 degrees. This is just clean heat that we are generating, clean green heat that we are generating on the surface just by putting the coating in sunlight. And the sunlight absorbs the material and converts it to heat. So there is this photon to phonon, and phonon gets manifested as heat energy through this at the surface of this coating. And again, we wanted to understand a little bit about why this the temperature that we are reaching is significantly higher than other materials. So we wanted to understand that. So we have done a variety of fundamental characterizations. Say, for example, this is the SEM cross section of this material. So imagine these are three-dimensional spheres, nanospheres, and you break them open like you crack the sphere, and that allows you to see what is inside the sphere. And this cross section actually resembles very closely to a Japanese kind of a origami fan, which is basically has a broad mouth or opening on the surface, and that is continuous and extends all the way to the center of this material in the form of a continuously graded pore structure. So if you can kind of imagine the structure, you take a cone and then assemble this cone one against each other in a 360-degree fashion, you get this entire structure, the three-dimensional structure, isotropic structure. And so that is important in not only giving that is manifested as a very high surface area of this material, about 1,200 meters square, but more importantly, this is what helps in its large absorption. Like I said, this reflection is almost next to nothing, transmission is nothing, and even the scattered component is nothing, is very, very low across the entire spectrum. That means it absorbs the photons very efficiently. And one of the reasons why it absorbs is because you have this cone, like I alluded to previously. You have this cone which is forming something like close to a unit cell. And now if you try to put a photon in any direction in a cone, inside a cone, it is only going to get internally consumed, through multiple, something like a multiple internal reflection channel. It is going to get internally reflected and consumed and not come out. That means the energy is hardly any dissipation happens. It is completely thermalized. The photon energy is completely thermalized and internally consumed by this material. And that is what gives us an alpha, which is the absorptivity, which is very close to 1, whereas the emissivity, again, from these because of this cavity geometry, the emissivity is around 0.3 to 0.4, which is actually violating the Kirchhoff's law of thermal radiation. And you know that this kind of violations are very well known in literature, because cavities are one of the best absorbers and one of the poor emitters. But when it comes to applications, this low emissivity is actually important, because low emissivity actually at a larger scale, at a macroscopic scale, means that the radiative loss from this material, the way when something heats up, it always radiates and gives out its energy. This is coming from all the way from Planck's law of thermal radiation. But when the emissivity is low, what it actually means is that the energy which is lost as radiative loss pathways from the material is actually low. And this is something which is very interesting for us when we think of applications. And we have done a lot of spectroscopic and microscopic and kind of understanding, or introspected the structure with a lot of complementary techniques to arrive at the final structure, which is basically a combination of short-range ordered, which is graphitically ordered domains, which are in turn disordered in the long range. So this kind of structure is in the literature is called hard carbon structure. What is already known is it's a hard carbon structure, but what we have done on top of the hard carbon is induced these well-defined pores to give it that particular morphology, which is very important. So again, this is, I'm not going too much into the details, but I would be happy to kind of elaborate this during the discussion, that this structure is actually important for it to give a very high photon to heat conversion efficiency. And what is that efficiency? Basically, you put in a given amount of light energy. You know that there is this convective loss and radiative loss and convective loss, which a material has to lose energy. And so you take all the energy, do an energy balance, and see at the end of it, what we estimate is basically how much of, for a given amount of light energy that is incident on this material, how much of it is actually manifested or converted to thermal energy or heat energy. And that comes to a staggering 90%. This conversion of light to heat at 90% is something very unique, because like you see from the slide, the existing solutions, like say, for example, the rooftop solar water heaters and other forms of titanium nitride, a lot of different materials are there, but their conversion efficiency is close to 70% at the best. This is the best case scenario. Whereas for NCF, we are already touching 90%. And you can see that clearly from this kind of a graph where you have mapped graphene, activated carbon, different allotropes of carbon, and NCF being the material that we have made is actually one of the highest surface temperatures, yields one of the highest surface temperatures. And this is also captured in this short movie that I'm going to show you, which is basically a thermal movie. This is captured using a thermal camera. So you bring in a laser pointer, which is normally what you use for a laser presentation, PowerPoint presentation, or any presentation, and you try to draw a symbol on the surface, and you can see that it creates a beautiful the heat map signature. So as the laser pointer comes in, I'm just running it again, you see a hotspot that is being created, which is resulting in a temperature difference of already 5 to 7 degrees, created by just a laser pointer, which is about 100 milliwatts in power. So this is, again, going back to the exceptionally high conversion efficiency the material has. We have done a lot of other tests. I'm not going into the details of this, but saying that because it's a carbon material, it is going to give you a lot of stability of function. And especially when you look at solar to thermal energy conversion, this is going to be one of the best materials. So now, with that as the background, I'm now trying to go last probably 10-15 minutes, maybe 5-10 minutes I'll take to impress upon you the applications or the products, technologies that we have been able to develop. That was the science part of it. Now, when you look at the carbon dioxide emission, I know this is an important aspect of sustainability, the global warming, and everybody is now bothered about carbon dioxide emission, the amount of concentration of CO2 in the atmosphere. But in very interesting and shocking statistics that we came across was 45% of the global CO2 emissions actually comes from heating air and water. These are just two ubiquitous things that is everywhere around us. You start heating them, you emit carbon dioxide in the process, because most of the heating sources that we have are non-renewable sources, which means that you end up putting CO2 at the same time that you're generating heat. This is accounting for the 36 gigatons of CO2 emissions from heating alone. So now we thought that in this context, the heating that we are generating by purely solar thermal using our NCF material is something which is going to be extremely useful and relevant, because it comes with zero CO2 emissions. There is no CO2 emission, but at the same time, you produce heat on the surface. And now it becomes any heat on the surface now becomes an engineering problem. Or how do you take that heat and use it for put it to use, or put it to do a job for you? And so the first example that we did was take up this hollow kind of aluminum tubes, bend it around in the spiral fashion, and coat the inside of this. The idea is that these are hollow aluminum tubes, so you can flow water through the inside of these tubes, put this in sunlight, and so this heat, which is now taken generated by the coating, is now able to transfer through aluminum, because aluminum is a good thermal conductor, and we should be able to heat water through that. And that is exactly what this video shows you. That and now we developed a prototype. If you see, we are measuring the temperature of water at the outlet, and you can see that the temperature reaches close to 80 degrees. In fact, we are able to cross 80 degrees. This is nothing water heating with no other energy but sunlight. And because we are able to cross 80, something interesting opened up that, and a device like this, which is about hardly 1 feet by 1 feet, device weighs about half a kg, can give you an output of 50 liters of water per day. And basically, this is again zero cost heating. And what we did was, if it cross 80 degrees, that means we can get rid of biological material. We can get rid of pathogens. Most of the pathogens are unstable at this temperature. So we ended up doing some experiments where we take some known concentration of pathogens and try to kind of see what happens when the water comes out. We see that the kind of all the pathogens, even in spite, if we start about 10 power 6 CFU per ml, concentration, we end up getting almost next to nothing in the output water. So this is again something which can give you a method, a clean and a green method, without adding any CO2 to the atmosphere, without contributing any CO2 emissions. You can get water heated and purify water, at least get rid of the pathogens. And like I said, this is one of the lowest CO2 footprint for heating water itself. But this is one of the things. But water heating or killing pathogens alone is not going to be enough to declare that water as pure or potable. So what we can do, what we did in the next case, is go from heating to actually boiling water. And again, I'll probably skip some of these slides again due to lack of time. But what we did was, we developed a concept of interfacial heating. Of course, I should here definitely acknowledge the contributions from Professor Neil Cameron in Monash, who's been a wonderful collaborator. So he was the one who made this polymeric membrane or scaffold, porous polymer scaffold. And we took this scaffold. What was interesting is it's a porous structure, and we coated this one surface of this material with NCF, that is the black material, that is our proprietary material. And the interesting thing about this is, if you take this material and try to kind of dunk it into a body of water, it self floats. It's so light and porous that it can actually float even if you push it down inside the bulk of water. And this was interesting because this gave us an opportunity for interfacial evaporation. So you take this material, it naturally suspends itself at the air-water interface. This is the interface where the sunlight reaches the coating. Water reaches it from bottom, and you can see this droplets of water which are now dye-coded and evaporating from the surface, because it is now able to pick up the heat from the NCF coating and able to evaporate and form water vapor. Of course, we needed to, in order to see it better for a visual effect, we have added some dye molecules. That's why you see these water droplets or water vapor droplets as green in color. We have just added some rhodamine dye to it. And so we went on, and again, pure water in lab scale is interesting, but when you talk about direct applications, salinity or dissolved salts in water is one of the most important and difficult to remove contaminants of water. And when we evaporate water, at least what we saw is, with 90% efficiency in the solar thermal conversion, our rate of water evaporation is about, we could reach about 6 to 6.5 liters per meter square per hour. Again, when you benchmark it with the conventional solar, still it's just doing 1 liter per meter square per hour. So we are already doing about 5 to 6 times higher than a conventional market-ready solar still. But again, we have done a lot of different tests to prove that the salinity is actually rejected. What happens is, water vapor evaporates and the salt is all left behind. But because the salt is left behind on a well-defined membrane, we can now take the membrane, clean it, and put it back for use. So every day you take the membrane out, put it, clean it, and put it back, you are good to go. And this can be done in the evening when the sunlight is not available, and we can get as high as 90% salt rejection from this interfacial coating, which we have also established through detailed COMSOL kind of simulations, where we see that the heat is basically restricted only to this interface and not into the bulk water. So we are selectively heating the water at the interface of at the tri-interface where light meets NCF meets water. So this combination of light, NCF, and water is very powerful, because light is able to interact with NCF. provide the required temperature, and that temperature is instantaneously delivered to the water for it to evaporate. Now, this is evaporation, like I said, is only half the story. What can we do? I'll just quickly go through this. So what can we do to really take that water vapor and recondense it back? That is where we get pure water at the end of the day. And this is entirely captured in this beautiful paper which in 2015, which says solar water productivity, which takes into account how much of sunlight is available, how much of it is converted to thermal energy, which then goes on to produce vapor, water from water, liquid water to vapor, and then not only stop there, but take also into account the water vapor thus produced, how much of it can be recondensed back to liquid water. So this entire cycle is what is accounted for in the solar water productivity cycle. And therefore, like I said, we don't want to go into the conventional solar still again. So what we did was completely different. We reinvented a new design for the solar still, where you see that the NCF coated surface, right now we can make 2 meters square. This is how the surface looks like. So now we have heat transfer tubes, some heat transfer fluid running across all along the surface. This surface, when you put it in sunlight, gets heated up. Now the heat is actually transferred from this, the heat is actually transferred from this through a heat transfer fluid into a body of water, which then condenses. By doing this design, what we have actually done is decoupled the heating part and the water condensation part. Remember, this was the limitation in conventional solar stills. The same surface is the light admitting or the heat generating part and the condensation part. We kind of decoupled it because we want to go higher in energy efficiency. And so we can basically go from decouple this. And now we work with like a mechanical engineer heat transfer problem. So how do you transfer the heat generated on this surface to the water? Once you do that effectively, the water starts evaporating and condensing. Not only that, once the condensation is an exothermic process, so we can use that heat to heat more water, and that builds the second stage. That's where the second stage comes in. Now you have condensation happening not only from the first stage, but also from the second stage. So your cumulative water collected is going to increase drastically. And what did we see? We could see that the clear water output or clean water output is about, in field experiments, about 30 to 35 liters in a day, which is significantly higher than what a conventional solar still would do. And we have now redevised worked on the engineering design so that we can even go from seawater to pure water which is less than 100 ppm. And we again re-emphasizing that we have the lowest energy and therefore the lowest CO2 footprint for the entire process. So this is basically the summary. We can generate now clean water. And the best part is, because it's completely dependent on solar, we are not depending or tapping into any of the energy, other forms of energy, like electrical. We're operating purely on solar, and that's free energy. Therefore, our energy footprint is very low. Consequently, our carbon footprint is very low. So what are we doing? We are not stopping. There is no point in stopping in the lab. India is a place where you have plenty of research problems to work on. So we identified that this particular area in the western part, which is close to us, is one of the most water scarce area. This is the Bhuj or the Kutch area, where most of the salt of India gets manufactured. This is a salt desert, so as to say, of India. And this is where the water problem is really high, because the water salinity touches almost 5,000 ppm, and that means reverse osmosis just can't work at that high salinity levels. So what we are doing is, right now we are in the process of setting up a 300 liter per day completely solar thermal water distillation unit in this Kutch area of Gujarat, which is going to, on a pilot scale, we are testing it on about 100 school children who are going to get benefit from this 300 liters production per day. And this, we think, is going to make a small change not only in the living conditions, but also in the health of our future generations. And remember, all this is being done in a very sustainable way, because we are not using any other source of energy which is polluting. any other polluting form of energy. So with that, basically, this is one of the things that my research group does at IIT Bombay. We also work on energy storage, environmental monitoring is something which we are very passionate, and other forms of green hydrogen and so on and so forth. So we are working largely in the energy and interfacial environment, in energy and interfacial science. That's what we do. You're free to write to me. This is my group. I'm kind of all along I've been presenting as if I did the work. The work is completely done by my wonderful set of team and my students. Like I see, I'm right at the background. These are the people who have been running the lab and doing the work, and I've been just sharing the data with you. Thank you very much for your patient listening. I should be thanking my funding agencies, and this is the NCF Labs is the startup that we are working on, particularly in the solar thermal domain. So with that, I'd like to stop here. Thank you for your patient listening, and I'll be happy to answer any questions. I hope I have not exceeded my time limit. I just try to push it as much as possible.
I think you are on time. Thank you so much for your wonderful presentation. Specifically, I mean, targeting the energy transition, which is really the critical need towards achieving the Sustainable Development Goals. And project mostly focused on the energy, your energy intensive areas where actually transition can really mean a lot to the planet. We have a
Yes.
few questions from the audience. First from Dr. Anita. So
Yeah,
she's
please.
asking the source of the carbon material that has been developed, and she also wants a bit of clarification on the hard carbon versus soft carbon and how
Okay.
it is suitable for desalination.
Okay. Yeah, sure. Thanks. What the first question is for the making the carbon the NCF itself. What the source of carbon to it is basically acetylene. We use acetylene, send it through a furnace where it's at about 600, 700 degrees centigrade. This basically acetylene breaks down. We are not sure whether it's a homolytic or heterolytic cleavage, but at the end of the day, it ends up producing carbon precursors, which then deposits all along these fibrous silica structures. So by controlling the best part about CVD is basically you can control the conditions like flow rate, temperature, the amount of gas that you pass, and all these. By controlling that, you can control the thickness and the uniformity of deposition, and that is what we have optimized. And once that carbon material, the entire surface of SiO2 is coated with carbon, all you need to do is take it out and put it in sodium hydroxide. It will react with the silica. It will etch out all the silica, forming solubles or water soluble sodium silicates. So what is left behind is an integral carbon structure that we have. So the second question about the hard carbon structure. See, the hard carbon is something which is interesting because see what when you say as the popular saying goes, diamonds are forever. But if you ask me or any scientist, diamonds are not forever. Diamonds are the metastable form of carbon. What really happens is every single form of carbon gets over time will collapse into the thermodynamically stable form of graphite, which is basically the carbon that is found everywhere on Earth. It's graphite. That's because graphite is the thermodynamically most stable form of carbon. But there are certain forms. And so, for example, you take carbon nanotubes, graphene, onions, carbon onions, or Buckminster fullerenes, any form of diamond, nano diamonds, any form of carbon allotrope, you heat it up, it will collapse to graphite. Now, there are also certain forms of carbon which resist such graphitization, and those are called as hard carbons. It has nothing to do with the mechanical property; it is to do with the thermal stability. And what like this cartoon shows you, these are basically short range. At the short range, you will find them as they will behave as graphite. That is, they are well-ordered graphene layers sitting one on top of each other, interacting through van der Waals interactions. But when you go to the long range, this order collapses. So it's somewhere neither a completely amorphous material nor a completely crystalline material. It's a mixture of amorphous short-range ordered domains, which gives it a certain amount of crystallinity, and which then breaks down over the long range, which gives it a certain amount of amorphosity. So this combination actually resists crystallization or graphitization, rather, because the entropic penalty that you need to pay to bring all these disordered domains and make them align in the form of a graphite is way extremely high. And therefore, these resist graphitization, and therefore these are called as hard carbon structures. And these are structures which are basically important for solar thermal conversion. That has been our observation. I hope I answered the question. Dr. Anita,
so,
if you
sir.
have anything. Yeah.
Yeah, Dr. Anita has asked further question, but before that, I'll take up the question of Professor Fran.
Sure.
Also, meanwhile, if anyone else has have other questions, may please type it down in the chat. So Professor Fran has asked, since it's about desalination, it already has an implication in desalination. Can these materials also prove useful in isolating minerals, for example, lithium from bryons? So from electronics
Absolutely.
perspective. So a bit of elaboration
Yes.
on that.
Yes. In fact, we just that's a very relevant question. IIT Bombay, we have just started entire program or center of excellence which looks at critical mineral independence or self-reliance. One of the projects that we are taking up is, can we now use this solar thermal desalination to enrich, say, lithium from seawater? And if we go down into the seabed, the nodules, the polymetallic nodules in the seabed are rich sources of cobalt and nickel. So we are trying to look at this angle very carefully. Yes, but the answer is yes, we can enrich to a certain extent. I don't think we would be able to completely recover lithium, but we would enrich lithium with a certain amount of other sodium, potassium, magnesium, and other salts, which then can go through a process of refining to get lithium at the end of the day, or lithium salt at the end of the day. But then, like I said, the seawater is an infinite source of lithium, and therefore that's very well in the pipeline. Thanks for that.
Another question that we have is about the stability of these carbon structures at high temperature and in air.
Yes. So carbon. So I don't have the thermogravimetry, but if this is basically because it resists graphitization. If you heat it in an inert atmosphere, the structure doesn't, or the structure of the material doesn't degrade even at 2000 degrees centigrade. But when you heat it in oxygen or in air kind of environment, the minute it starts going near 450 degrees, it's end of the day carbon. You can't change elemental carbon behavior. So it's going to react with the oxygen present in the ambience and form CO2. So it's kind of stable till 400 degrees centigrade, which is good enough for the applications that we are targeting.
Okay, thank you so much, sir. I think this answers the questions. Another part is about the environmental impact, since at the end of the day, we have to achieve, we are targeting sustainable development goals. So do we have the numbers about CO2 emissions, and, how is it comparable to other, in terms of energy efficiency and stuff?
Yes. Of course, yeah. So there is this. Let me just go to the slide. Probably I kind of streamed through it. Yeah. So this is where the energy consumption is looking at. Say, for example, we have multi-stage flash distillation, reverse osmosis, nanofiltration, electrodialysis. All of these are very prominent and indeed scalable commercial technologies for water purification. But if you look at it, basically for the energy consumption is given is watt per liter. And here we are talking about anywhere between 3 to 15 watt per liter, whereas ours is one of the lowest in terms of energy consumption. The other thing that I want to point out in this energy consumption is basically all these black techniques, the ones given in the black, are constantly require energy, electrical energy, to be fed into it for the process of water purification. Here, it's all dependent on solar, and that is why we have one of the lowest carbon footprints and energy footprint. If you just go with another statistics, which is used for just heating water, if you look at the carbon footprint, you have, I can show you this slide, which is basically the CO2 footprint in gram per liter. If you want to say, take 1 liter of water and take it to 85 degrees, what's the CO2 footprint? This is going to be extremely low. And this footprint, which is roughly about 5 grams per liter, compared to, say, something like a coal stove or even industrial boiler, is 1 order of magnitude lower. Also, this is a one-time penalty. This is still a one-time penalty. It is not a continuous penalty for as compared to all the other techniques. That means you have to continuously use boiler. You have to feed in fuel continuously. Whereas here, this carbon footprint comes purely from the making of the material. Once the material is made, it's largely very CO2, largely minimalistic CO2 footprint, because most of the energy is taken from the sunlight.
Thank you so much, sir. We are really grateful. As part of now the closing, I'll like to invite Juliana for taking it up further.
Yeah.
Awesome.
Thank you so much.
Thank you so much, Dr. Subramaniam. That was amazing. I was like thinking during your presentation, I was like, okay, we need to talk more about water and like what that means to the rest of the world. So thank you so much. That was awesome. Thank you for the discussion, Lavish, introduction. That was perfect. Had a wonderful time. And I'm just going to close the presentation with some opportunities for us to continue interacting. So if you don't know, Bombay 9 has a platform that we created with the ACS Green Chemistry Institute called Green Chemistry Teaching and Learning Community. And we do have a place for everything green chemistry education related. So if you want to continue the conversations from this webinar, if you have any other questions, if you want to talk more about the technologies that we talked about today, you can join our forum discussion over there. And I think Chloe added the link in the chat, so that's perfect. So you can continue the conversation over there. We'll be super happy to have you in the GCTLC. You just have to write your name, email, and then you're in. And on the next slide, I'd like to invite you for a webinar series that Bombay 9 has called Green Chemistry Connections. We have this moment every month to talk about green chemistry, interact with the community. So the series is starting on October 15th. So you can register through the QR code that you have on your screen. And every third Wednesdays of the month from 12 to 2 Eastern time, you'll be able to talk with other people around green chemistry, and we have different themes every month. So we're super excited to have you there in case this is something that interests you. On the next slide, I just have a call for a webinar series that's happening tomorrow in celebration for the green chemistry, the GCS Day, the Global Conversation on Sustainability. So as you can see, the IYCN together with IUPAC is organizing this amazing lineup of events. You have 3 sessions throughout the day. So depending on where you are in the world, you can join 1, 2, or even 3 sessions. So the registration link, Chloe just added that on the chat too. You can register for this amazing event that's happening tomorrow throughout the whole day. And on the next slide, I just wanted to invite you also to contribute to another project that IUPAC's organizing. It's a video competition. It's a video contest for undergraduate studies showing how chemistry can make a difference in human wellness and environmental sustainability. So the deadline is until next year, so you still have time to prepare your video, join the contest. And if you have any questions, Ollie is here in the call too. He can answer any questions. And also you can read the QR code who's going to take you to the project. And also if you want to learn more about this project, you can have access to it. So we're on time. This is great. I'd like to thank all of you for all of your discussions. That was awesome. Dr. Subramaniam, thank you so much for your presentation. It was really, really awesome to have you here with us. Lavish, you're awesome. Thank you for moderating, help with the project and everything. And if you want to continue the conversation, we know where we are. And and I hope you just have a great rest of your day, night, evening, afternoon. And thank you all so much for being here.
Thank you. Thank you so much. It was indeed an honor being a part of this. And I really want to continue my association with being benign and being beyond benign and IUPAC. And thanks a lot for this wonderful opportunity.
Thank
Let's
you.
keep in touch.